base ket. Base kets are like orthonormal unit vector in vector space in 3D vector space. Any vector in 3D space, 3D vector space, any vector can be represented by orthonormal unit vectors. Any vector V can be represented by orthonormal vector V any vector equal to summation of I unit vector into V dot unit vector. This is the projection of the vector along EI vector. Similar to this orthonormal unit vector in quantum mechanics, we can write any state that is ket vector in terms of base ket. That means now these base kets follow a property which is called completeness or closure. Now what it is completeness? That means if AI are the base kets, then they will follow the relation summation of I AI I equal to identity operator. If any ket vectors follow this property, we will call these ket vectors are the basis of this vector space. Now it is the discrete condition. Now if the vector space is suppose continuous and suppose x are the continuous base kets, then the closure or completeness relation will be integration minus infinity to plus infinity dx x x equal to I dt. Now what completeness or closure relation means? Physically it means the physical meaning of this completeness is we can represent any state in terms of base vectors. How we can do so? Suppose that alpha is any state or ket vector. This means we can operate with identity operator. It will do nothing to the state. Now as we know that I means I, AI, AI. That means summation of I, AI into AI alpha. As we know, this is similar to the 3D vector. This is like ortho normal unit vectors, and this is the inner product, which is means the projection of alpha in the basis of AI. Now similarly, the same meaning is also true for continuous base kets, which is alpha can be written in terms of continuous base kets x dx x alpha. This is also true for this continuous base kets. Now we'll see that any operator any operator can also be represented in terms of base kets. How? Suppose x is an operator, then we can say that this means we can multiply a identity operator with x, which is nothing but summation of I ai into x, and we again write operator from the right, and which does not change the operator at all. Now again we can write I j ai x aj, which is nothing but ij ai x aj aj. Now this is nothing but a constant number. How we can see that? That operator on a state will change the state. Suppose it is gamma. Now that means ai x aj is equal to ai into gamma, and this is the inner product between two ket vectors, and which is nothing but a complex number. Then we can write that x equal to summation of I j ai x aj into ai aj. This is the outer product between the two ket vectors, and which is an operator. So we can write any operator in terms of base kets, and from this similar relation we can also represent an operator in terms of matrix. Suppose that there are n base kets, then we can write x in terms of matrix. This symbol is represented by. Then any operator can be represented by in terms of a1 x a1 a2 x a1 dot 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 a2 x a1 a2. Similarly, we can represent any operator in terms of matrix. Now I will give two examples of continuous state and continuous operator, which is very important. Continuous state and continuous one example of continuous state is the position which is represented by x. X is the position vector, and the operator that will operate on this state and give back the position, that means this is the eigenkets of operator x, which is a position measurement operator. If it will act on this position ket, it will give the position and the state will remain same. Another example is momentum operator. P, and the eigenkets corresponding to this operator is P. If this operator operate on these eigenkets, it will give the momentum and the state will remain same. Now both the position kets and momentum kets are base kets. That means it will follow the closure or completeness relation. That means minus infinity to plus infinity dx x will be identity, and minus infinity to plus infinity dp p is identity. Now we can represent any state vectors in position. Now we can represent any state in position space or momentum space. If some state is alpha, we can represent it in position base case as follows. Similarly, we can also represent the same k vector in momentum space as follows: dp prime, p prime, p prime, alpha. One important point is here we cannot represent spin state in terms of either position or momentum. Since spin is a quantum mechanical concept, it has no representation in position or space.